Thank you very much, Professor Neelima. This is a great opportunity once again. It's a return to ICTS after 6 years. I don't know if I can change that return level to probably 2 years or 1 year. It's a fantastic campus. And of course, a great audience. Good afternoon. Today you've been hearing quite a bit about networks. And this is a transition from the previous talk to back to networks. You heard Udit speaking in the morning a lot about networks, and he said networks are everywhere. I hope you saw them during your lunch and wherever you went out. They are indeed everywhere. And you also heard Dr. Ambika talking about recurrence networks, right? So I will be focusing on a class of networks called causal networks. Of course, I'll try to keep the context within climate. I belong to the Department of Data Science and AI at IIT Madras, and I'm also with the Department of Chemical Engineering at IIT Tirupati. So you will hear a lot more about the methods and with, of course, some applications to climate data. I do collaborate a lot with Udit on the climate part. So the whole idea is to give first an overview of networks very quickly, and then zoom into causal networks, talk about how they are reconstructed, go into the subtle aspects which quite often students don't get to, or beginners don't get to know very easily. Although you have ChatGPT, everything to skim for you today, still you cannot trust those results. So I'm going to talk about the basic premises behind some of the very popular methods that are used in reconstruction of causal networks and caution you on certain things. And particularly we'll focus on the two broadly used classes of methods, quite competing Granger causal networks and Convergent cross-mapping, CCM. And of course, we'll talk about a bit of the synchronous networks that Udit talked about towards the end. So when it comes to networks, I just want to take you one step back into systems theory. Yeah, you can say it's linear systems theory, but you can also think of nonlinear dynamical systems, which has been the backbone of many building models for many processes. But over the last, I would say about 15, 20 years, network models have really taken the world by storm. They're not new. If you have heard about graphs and graph theory, they've been around for a very long time. Networks are a modern name for graphs. And I heard that some very popular group in the US says the difference between graphs and networks is if you have more than perhaps 200 nodes, it becomes a network. Anyway, so there are courses on network science, and we teach a course on complex networks at IIT Madras under the complex systems dynamic center. So why are these networks very popular? I'll just highlight perhaps 2 or 3 main advantages. One, they do not ask for a detailed set of ODEs or PDEs like your classical models, okay? So which means that you can simply model the structure and not worry about the finer details. And that's very attractive from a data science viewpoint, because if you ask the requirements on the data to reconstruct the skeleton of a process, it's a lot more milder than actually estimating the parameters of the model. So from that viewpoint, network models are very attractive. Secondly, they allow you to represent all kinds of relationships in a very hierarchical manner, which means you can start all the way from a skeletal structure and start building information layer after layer. So you can have the simplest is an undirected, then the directed, and then you have weighted, and weights can be transfer functions, or they can be even more informative and so on. So they allow you to encode information about dependencies in a very hierarchical manner, and you choose depending on the application. When it comes to climate models, you will find undirected networks, directed networks, and sometimes these undirected networks are also called correlation networks and so on, because correlation is a symmetric measure. So that is not possible with classical models. Classical models are boom, full detail all the time, right? And then you have to sit and extract the structure. Thirdly, the network models are very good because there are powerful graph mining algorithms. So that's very, very advantageous. these networks, like Udit pointed out in the morning, have a lot of properties. So if you're building network models, you do want to mine the network. So there is determining the network and then there is mining the network. You want to really use the graph theoretic properties of the network all the way from adjacency matrix, the eigenvalues of the Laplacian to degree centrality, everything. But which property applies to your application again and how you relate to the physics of the process remains a big open area. And a lot of research needs to be done in that respect. Okay, so when it comes to networks, seriously, very, very importantly, you should know your network. You should fill your KYN form, know your network form, because from a distance, all networks look alike. What sits at the node and what is encoded in the edge can vary tremendously across applications. So you have complex networks on the built on time series typically. And they came about really on time series about 10, 15 years ago, because nonlinear dynamical systems are beasts. They are not as easy to handle as linear time series, linear processes. So people started asking if I can derive certain characteristics of nonlinear dynamical systems, such as Lyapunov exponents and so on, and correlation dimension and so on from the network properties, and perhaps even more. So you will find thousands of papers, or I would say hundreds to thousands of papers on relating using network properties to, for example, determine the onset of Alzheimer's, or it could be in determining the onset of turbulence and so on. So you heard about phase transition. So again, that's a huge area of research. Get into it. I personally believe that these network properties have a lot more to offer than what you see currently. Now, if you're looking at another network, systems could be sitting at the nodes, whereas in complex networks, signals could be seated at the nodes, and the edges denote dependencies. There are networks built on univariate time series where data points are sitting on the nodes and the edges denote correlations or dependence between the time instance of a signal and so on. So you can have multi-layer networks where this could be a climate network, this could be an infrastructure network, and you can analyze how changes in climate network percolate to infrastructure network and could have a healthcare network and so on. So you have network of networks, if you wish. So depending on how complex a paper you want to publish, you can choose your network, okay? The probability of your paper getting accepted gets better. I'm just joking. Okay, so when it comes to complex networks, at least in this talk, I'll just focus on this 4 progressively sophisticated class of networks, starting from so-called undirected or correlation networks, so to speak. Both are undirected, but the difference is this suffers from confounding. So each edge denotes only pairwise correlation. You do not know if it is mediated or not. Once you resolve confounding, you run into so-called partial correlation networks. This partial essentially means the synonym for that is conditional, okay? And then you have the directed networks. Again here, the directed one, edge is both directed and free of confounding. And finally, you have weighted networks. But these are not the only ones. But these are very popular. And you can really progressively build this and get information about the process. And we have used these networks to build, for example, networks between weather variables or analyze interactions between variables in a large chemical plant and so on. So there are many applications that our group have been looking at. Okay, so why do we want to reconstruct networks from data? Why can't I build networks from the equations that I have? Yes, there are many methods that give you that. Yeah, you say, give me ODEs, I'll build network for you. But unfortunately, the class of processes that fall within that realm is very limited. Many processes increasingly are becoming so complex that you can't even think of writing any equations. You say, forget it, I'm just going to mine from data because you have such powerful algorithms for reconstructing networks from data. Well, apart from that, you can calculate strengths of connectivity, which is very difficult to do so from first principles models. I'll give you a very simple example. If you take a telephone network within a campus, ICTS, IIT, you take an institute, theoretically, they're all connected. But practically, are they all active? Right? That depends on who talks to whom. Just like our brains. all connected, but how many really, how many connections are really active? Anybody can take a guess, but it's a very low number. So if you want to determine the strengths of connectivity and so-called effective connectivity, that's very popular in neuroscience, you have to turn to data. And it is a data that can account for stochastic effects and uncertainties. And very importantly, today, it's not about just knowing the model from first principles or reconstructing from data. It is usually your situation is at a mix. You know some information a priori and you have data and you want to blend. The shade of how much you know a priori and how much you're going to really extract from the data varies with the application. But there is that provision for partial knowledge. And it's better not to take an extreme stand. It's better to be really balanced and say for for climate applications, yes, there are a lot of models, but it's so complex that none of these models really fully help you understand. So that's why people have turned to data. So the physics informed or physics guided, there are so many knowledge guided ML algorithms are trying to fuse these two in different ways. Okay? We'll not go into those details, but that's essentially the advantage of turning to data. Okay, so when you are really turning to data, extremely important to pause and ask, what are the assumptions that I'm making about the process, about the data, and if you're building a network model, about the network, right? So I'll have to choose a measure that I'm going to encode in the edge. I'll have to choose a framework. Am I going to use a probabilistic framework, predictive framework, bivariate, multivariate? That means pairwise or all variables together and so on. And then, of course, I need a method of inference, estimating from data, and then a set of rules for constructing the network. So all these things are required. Any paper that doesn't talk about this, either you should ask, and if you don't get answers, don't give too much weightage to the paper. So there are many types of processes, and please understand what framework your process. You take climate process, people say it's nonlinear dynamical, but is there a consensus on whether it should be deterministic or stochastic? Not really. Is it a hybrid? Maybe. So there is no consensus, but it's better to be open-minded and say, well, it's nonlinear, deterministic plus stochastic effects, right? And is it time varying? Maybe, depends on the time scale that you're looking at, and so on, right? And when you look at data, you have to worry about measurement errors, missing data, small sample sizes, extreme values, so many things. And this takes quite a bit of time. So we were doing a project recently for ISRO for predicting crop yield. It took about a year to put the data together, to package the data together. The rest of the model building took about 6 months or so, but it is the data preparation that takes time, okay? So this is just a table giving you an overview of the different types of networks, but this is not exhaustive. There is a nice review paper. I've given the reference at the bottom. I absolutely have no problem sharing the slides. They have access to that. And as you can see, so just to help you understand the table, the name of the network in the first column, what sits at the node, what sits at the edge is described here. And very importantly, whether it's a directed or an undirected, and whether it is a bivariate or it applies to bivariate, a multivariate or univariate is given in the last column, right? So if you take correlation network, for example, we know that, so if you're constructing correlation networks, typically the signal or the state sits at the node, and the correlation coefficient is used to characterize the edge. And because it's correlation, it's undirected network, and it can be applied to multivariates, but you apply in a pairwise fashion. Although it is multivariate, you apply in a pairwise fashion. And causal networks, which I'm going to discuss a bit more lot more in length today. Again, it is the nodes carry the signals. Now you will need a causality measure that is encoded in the edge. And because all causality measures by the definition are asymmetric, you get a directed network. And again, it's a multivariate thing. Scenario, so you can have a pairwise or a multivariate causal network as you wish. You heard about epsilon recurrence networks in the morning before lunch. And again, what sits at the node, at the edge and node, and what characterizes the edge and so on is given here. And there are many more. Visibility graphs, for example, are becoming very popular increasingly. And there are a lot of theoretical results on how these graphs will look like for some standard reference signals, for example, white noise or IID, or correlated, if it is an autoregressive process, how is the network property related to the nature of the correlation and so on. So there are some nice results given. You can go and look up. Of course, we are not going to talk about this. You heard about recurrence networks very nicely in the morning, and then we'll talk about causal networks. Okay, so let's plunge into causality. Typically, I talk about correlation, partial correlation, and then causality in sequence, but in the interest of time, I'll go straight to causality. And causality is a very philosophical aspect that people have been discussing for centuries, perhaps. It is based, of course, on the cause-effect relationship, but when it comes to quantifying this from data, you need a good formalism, right? And you'll have to worry about causality in the time direction and causality in the variable direction. And if there is a space, then there's a spatial direction and so on. So when it comes to temporal causality, there are, broadly speaking, three forms. You have lagged causality, which is known as strict causality, where the cause effects results in an effect after some time. Instantaneous, as the name says, the effect is instantaneous. Bidirectional, both ways, right? Why do we need to know this? Because when you pick a method for reconstructing causal networks from data, you have to really ask, what is it capable of? Can it actually handle instantaneous causality? Can it handle direct? Can it handle bidirectional? And so on, right? And when you're looking at causality in the variable direction, again, you have choices. You can choose to identify pairwise causality, which is not free of confounding, or you can choose multivariate causality, which is built after resolving confounding. That means you discount all the mediated effects. So how do we detect all forms of causality from data? There is no measure, there is no method of inference that can ever claim to detect all forms of causality. Any method will have to subscribe to a measure that will encapsulate only one aspect of causality. So you have to be very clear depending on your application. So if you look at climate networks, I'll show you some samples. You will see predominantly what they have subscribed to. But here is a table, in fact, split in 2 slides, which again, I wouldn't claim to be exhaustive, but there have been some excellent papers, survey papers recently. You can find them in archive. So again, what is this table giving you? The type of causality. Okay, that means the measure, the mathematical measure that is being used to capture the causality and the description associated with that method. And then, of course, its limitations and so on. Obviously, we won't go through every row of this. But if you take Granger causality, which is very popular. By the way, the moment you pick up any paper or book on causality, one of the classic references that you will see is to Julia Pearl's work on causality, which was in 80s. Now, what happens is there are some issues with that. One, it is actually not the first work on causality. In fact, you can go back even perhaps 20 years before, where Granger, who is a Nobel laureate in econometrics, and even before that, Wiener, who was a pioneer in engineering, electrical engineering, and so on, they have all talked about causality. Granger was the first one to encapsulate causality in a definition, and his causality is predictive based. His definition is very straightforward. Of course, we have simplified it today, but if you read his original paper, it's very nicely done formally and so on. First of all, he assumes a stochastic process to be purely stochastic. That means you can't really go and apply it to any deterministic process. He himself dismisses its applicability in his seminal paper. And secondly, he says that definitely cause should precede effect, which means that it is originally devised for lagged causality. It cannot handle instantaneous causality, right? And thirdly, it's a predictive form. What that means is, I will say signal Y or signal X causes Y. If it's passed, helps me improving the prediction of Y. But that doesn't mean that's the only way a cause can influence an effect. There are many, many ways in which, there are some variables which will only trigger and not participate in the evolution. So that's a different form of causation. Granger's causality will not be able to detect that, right? So some domain understanding is required before you apply any of this. But the most widely applied is Granger because, number one, it was the first to arrive and its implementation is very straightforward, okay? And then there is cross-mapping, which came about, in fact, it came in ecology. One was econometrics, other eco is ecology. This basically caters to nonlinear dynamical systems characterized by weak coupling strength. And I'll show you one piece of work that we've done to analyze how weak it should be for you to be able to apply convergent cross mapping. This is purely in the deterministic world. At least there is no mention of its applicability to the stochastic world. It assumes that you have a nonlinear dynamical system. And this is completely based on the reverse logic of Granger causality. What I mean by this is, while Granger causality says the cause should help you improve the prediction, convergent cross mapping says I should be able to recover the cause from the effect. Okay, so I have the effect with me. It's like saying I should be able to say something about the parent looking at the child. If I'm able to do that, then X is said to be CCM causing Y. I'll talk a bit more about that in detail. There are many other techniques that have come up, and each has its own scope and so on. We have also contributed to this chaos here. So, so those are the definitions, by the way. They are not even methods of inference. So for one definition, you can have many methods of inference. Look at how complex the literature is actually growing. You can draw a complex network for that alone. So if I take Granger causality, there may be at least 10 different methods for inferring Granger causality. If there is a paper that says, I have inferred cause and effect relationship and it doesn't tell you what type of causality, then I think you should really downweigh that paper, because they are not clear what kind of cause effect they are capturing, right? Simply applying a method and saying that this is what is capturing is not good. So there are many methods starting there are methods based in frequency domain. So spectral methods are very popular for detecting Granger causality. These were the early ones. Then you have partial directed coherence, which is also based in frequency domain. I'll just show you one simple illustration. And then there is direct pathway function, which has come from our group. And then there are so many other things. The last column tells you what type of causality it's detecting, right? And there is embedding-based CCM method. We heard about embeddings in the morning, and so on. And then there are, dyno tiers. Clearly, it promises no tiers in the name itself, which I hope so. It's not an easy method to implement, but it says no tiers. Okay, so I think you should read those papers. I don't have the reference here, but please ask me. I'll share the reference. A complete formalism of what a causal measure should encapsulate, what is meant by summary causal graph, window causal graph, and so on. Essentially, window causal graph means it's only detecting relations within a window of time. Summary is at any point in time, if the cause affects the variable, results in an effect, then you say, yes, it is causal. Okay, so here comes a very, very, 10 power minus 6 micro sample, or maybe even a nano sample of the results that you will find. As you're sitting there, you can search on Google. Don't ask ChatGPT, it's still not up to the mark. Give me the number of results on climate and causality. You will easily run into millions of them, okay? And you can really, keep grouping the results. But this gives you some idea of how active this field is, number one. And number two, there are papers that do not refer to networks at all. They're only concerned with discovering the drivers, and that's it. So they don't reconstruct any network. As a result, they're not really reaping the benefits of graph mining algorithms and so on. Then there are papers that use network properties in abundance. Like you heard Udit talking about a lot of networks that really exploit the nice properties of networks and so on. Okay, so anyway, I leave it to you to really pick up any of this paper and then follow the lead, but a very, very active field. So let me just zoom into Granger causality, the subtle aspects of it, and then show you some illustrations and then move on to convergent cross mapping. Okay, so as I said, Granger causality rests on 3 axioms. One, cause precedes the effect, which means it detects lagged causality, and cause contains unique information. There is no way you can verify this, okay? So you will just pray to God that it works, that it holds. And all causal relationships remain constant. This is more like a stationarity condition or a time invariance condition on the causal relations. So if you look at the original formulation of Granger, it is rooted in information theory. So it talks about conditional distributions and so on, right? That the information, the conditional information, if it doesn't change, then it is not Granger causing. So the definition is not on what Granger causes, the definition is what does not Granger cause, okay? But then it's too difficult to implement because the issue with probability distributions, information theoretic measures and so on is they require large data sets. Computationally, now you're talking about about 69, late 60s. We didn't have much of a computational power. So Granger had to really water it down and finally brought it to predictive causality, where basically he said, if I have two signals, then predict one using its own past and predict that using the past of the other variable in question. And construct prediction errors. By definition, they are stochastic, so the errors are not zero. And if the variance after incorporating the second variable reduces variance of the prediction error, then you say this causes the other. That's it, very straightforward. And then you construct this graph, okay? So that is how it was done. Starting from a pair of variables, gradually it was extended to handle multivariate, bidirectional, and to a certain extent, instantaneous causality. But let me tell you this upfront. My own experience in the last 17 years of reading the literature on Granger causality tells me about 80% to 90% of people don't even implement it properly. They don't even have a clue of what should be the stepwise procedure of inferring Granger causality. They use routines and they report, that's it. There is a very important procedure that one has to follow to be able to arrive at proper inference. But maybe who cares type. That is how a lot of results are. Okay, so one of the most popular ways of implementing Granger causality is to build vector autoregressive models. And these are very easy to implement because autoregressive models can be estimated using linear least squares estimators. And that's why they became very, very popular. But people didn't ask certain questions that have to be asked because one of the major assumptions is this uncertainty that is driving the signal should be spatially uncorrelated. So you have to test for that. If you don't, then you will end up with a spurious inference altogether. And that is why you will see conflicting. I have seen papers that say, yes, global warming is because of CO2 emissions, Granger causality, one paper. And then a couple of years later, no, it is not. Granger causality reveals it is not. So which means that neither of them have truly understood. I'm sorry?
Not by the same author.
No, fortunately not. Fortunately not. Even if it is the same author, I don't mind saying I made a mistake not correcting it, right? And the harder part is there is no systematic study of which method is applicable to which scenario. You're taking up a problem, you're picking whatever comes to your hand and then applying the method and so on. Okay, so it is very important to conduct a test on the diagonal structure of the sigma E, that is number one. Secondly, you're force-fitting this model onto some series which may not even follow this. So obviously there is a model misspecification. Unfortunately, Granger causality is very sensitive to not only model misspecification, it is sensitive to measurement errors, it is sensitive to subsampling, it is sensitive to so many things that your inference can be highly wrong, highly spurious or highly biased, okay? So one has to be really careful. Anyway, when everything nicely holds, then you can use many ways of detecting Granger causality. As I said, for example, you can directly look up the matrices, or you can use what is known as a partial directed correlation. So you have correlation, you have partial correlation, a partial directed correlation in that order. And then you have frequency domain measures, partial directed coherence and direct pathway function. I'll show you an illustration. So here, very simple time series data, 3 series, and the goal is to reconstruct the class of networks from correlation to weighted causal networks. I've not discussed what is coherence. Coherence is I think many of the physicists should know this. So coherence is actually a frequency domain version of the cross correlation. And what I'm showing you here are coherence plots. Ignore the diagonals. This is the coherence between variable 1 and 2, and coherence being analogous to correlation is a symmetric measure. So you will see the plots as symmetric. And the rule, so the red lines that you see are essentially thresholds, okay? If the coherence at any frequency, the x-axis in each plot is frequency. If the coherence is at any frequency is non-zero, then they are connected. Okay, why do we look at frequency domain? Because in a lot of applications like physics, neuroscience, engineering, and so on, I am not just interested in knowing if they are connected. I also want to know the frequencies at which they are really talking to each other. Okay, so just going by that logic, you reconstruct this so-called coherence network, which is confounded. But if you use partial coherence, that means it removes the discounted effect, then you get an undirected network still, but these edges are now direct. They're free of confounding. That means, yes, Z1 affects Z2 and so on. But both of them are undirected. Now, if I turn to partial directed coherence, which is one way of inferring Granger causality, again, x-axis is frequency, but because it's a directed measure, it's asymmetric. Ignore the diagonals once again. The off diagonals, again, apply the same logic. The columns are the causes and the rows are the effects. So based on that logic, you can construct this, you can reconstruct this network. I'm going to show you the ground truth. I'm just pretending the realistic situation, so I'm just starting with the data, right? So nice, so it has detected bidirectional relations, but it's still a structural network. There's no weight on it. But if you use a direct pathway function, you can actually attach strengths to the links, which will tell you how strong that link is. So here is the ground truth, right? These are the generating equations. Go ahead if you want to simulate this data. It's an Varma process, not Varma, vector ARMA process. It's very close to karma. So it's despite the mismatch between the generating process and the model that we have used, it has actually done a fairly good job. Now, this is not guaranteed all the time, okay? If the data size is very small, in many applications, you may not have the luxury, or if you're looking at a window of data, the data size may be small, then you have an issue, right? In that case, the model misspecification can cause a problem. You can refer to one of our publications on how to handle that. I can give you the reference later. But for now, yes, it has done a fairly good job. You can also use your surrogate analysis, bootstrapping, and so on to come up with errors on these weights and so on. I've not done that. Okay, so what are the known limitations? Many of them. It assumes stochastic framework. It assumes it's stationary. So the first test that you have to do is if your data is stationary, remove trends and so on. And there is no scope for handling deterministic only signals. And it's very sensitive to measurement errors. If you are filtering the data and inferring Granger causality, if you're filtering, for example, to remove noise and so on, then there is an issue. There is no direct provision for detecting instantaneous causality. In fact, you will have to construct what are known as structural VAR models after you have done the test on sigma E to handle that. And it can be quite sensitive to model misspecification, especially if your data size is small, or if you are fitting a linear, the VAR model that I showed you is linear, but if the data generating process is non-linear, then it can again go for a toss. And there are, of course, misunderstood limitations. It's applicable to linear process. No, that is wrong. Granger only said start with VAR models. In his definition, he is not restricted to any linear process. Okay? And it is only based in the predictive framework? No. As I told you, it began with the information theoretic framework. And there's no room for handling non-stationarities. That's not true. You'll have to remove stationarities and then apply. So, by the way, there's a very nice paper, beautiful paper that came about a few years ago, which does a very nice theoretical plus illustrative analysis of all this, many of these limitations. Please do read that up. Okay, they're all big names in time series analysis. Okay, so just to show you how do we handle missing data, and this can be something that you can do even in with any other method. So what do we do? We use the powerful compressive sensing ideas. I don't know how many of you have heard about compressive sensing. Essentially, it came about 20 years ago. It's different from your traditional compression. Traditional data compression, you compress after the data has been acquired. All your JPGs and so on, they're all compressed files. Compressive sensing, it compresses as it is sensing. And essentially, the idea is to sample randomly rather than to sample uniformly and then compress. So you go from many to few, compressive sensing recovery algorithms allow you to go from few to many, and that's how you handle missing data. So there are formulations of this. Again, if you want references to that, I'll give you. So I'm just showing you how we took a meteorological time series for Chennai, and then we throw away 30% at random, and this is how the time series looks like. And here is how the reconstructed signal looks like, and this is how the directed pathway functions look like. These are the same as you saw earlier. And this is the network that you get for the complete data. That means if I don't throw that, because I don't know the reality, the only reference for me is if I had the full data, what network would I construct as against what I have constructed with the missing data. And pretty close. Of course, this will get worse and worse as the percentage of missing data increases. Okay, so just to close the discussion on Granger causality and transiting to nonlinear dynamical systems, very relevant to climate. You can handle nonlinearities in many ways. One of the most powerful ways is to turn to machine learning to use a kernel trick, which essentially transforms the data into features, which mean features are essentially nonlinear transformations of data. So if I have a variable x1, x1 square, x1 cube, square root of x1, all these form the features. If I have multivariable, that means many signals, then all such nonlinear combinations are constructed in the feature space. And once you have done that, you can apply your linear technique. That's the kernel trick. So we did that. We proposed what is known as a kernel Granger causality. You can look up the reference in the Physical Reviews paper that was published. This is an example from a bioreactor. We're showing how the kernel PDC is able to detect the directional relationships. Again, you have the red lines which are derived from the data. They are thresholds, statistical thresholds derived from surrogate data analysis and so on. Okay, so I'm sorry. Yeah, I'll close. So let me just quickly, in fact, I can skip some of the slides because Ambika did a nice thing in the morning, so I'm going to skip. I'm only going to talk about the core idea of convergent cross-mapping, right? So when you are dealing with a nonlinear dynamical system, the biggest challenge is when you want to recover the states. Unfortunately, the states and measurements are nonlinearly related, and therefore you cannot recover the states uniquely if you don't know the model. You can only recover the phase space up to a diffeomorphism. That is the idea. And Tucken's embedding theorem essentially allows you to do that. Convergent cross-mapping really rests on that embedding idea and says that I will construct manifolds for each of the series that you give me, and I will cross-map X. So if I want to know if X causes Y, I will recover X from the manifold of Y. And if I want to know if Y causes X, I'll recover Y from the manifold of X using a weighted algorithm and so on. But first you have to do the embedding, you have to construct the manifold and all of that. Again, all the discussion that we had in the morning of choosing the lag and the dimension M, all of them come into picture. Okay, so what convergent cross-mapping does is, it says you cannot be, it uses ideas from estimation. It basically says even if you're given 1,000 points, start with 100 data points and calculate the cross-map skill. What is a cross-map skill? The correlation between the recovered X and the original series, okay? And you do that for both directions, and you do this for increasing number of data points. If it converges, let us say if it increases and settles down, then that means that particular signal is causing Y. For example, here, if X is causing Y, the red line here is corresponding to Y recovered from X. So you can see as the data length increases, the correlation between the recovered Y and the true Y is almost nil, which means that Y is not causing X. The blue line is for correlation between recovered X and the observed X. And the correlation increases and converges. So which means that you conclude that X causes Y, and likewise for the remaining two, okay? That's the idea. Of course, I'm going to skip the embedding part. Just one perspective very quickly, very few seconds I'll take. The whole idea of embedding is to account for the loss of dimensionality you have had in going from the state space to the measurement space. Your states live in obviously much higher dimensional space than your measurement. You could be measuring only one temperature and so on. But the actual states that are driving the temperature may be many. So when you projected the states to the measurement space, you lost the dimensionality. That dimensionality you'll have to recover by walking in time. This is a perspective that has to be kept in mind, okay? So how many steps you want to walk in time is the beauty of Tarkin's embedding theorem or all the embedding theorems. Anyway, so I'm going to skip this for the Rossler attractor and take you straight to shortcomings, couple of shortcomings, and then I'll conclude very quickly. So there are issues with original CCM. For example, computationally, it is not scalable, and there is no quantification of what coupling strengths over which CCM is applicable, and there is no formal study on the suitability of CCM for stochastic processes, and we don't know how to detect direct causality. So we addressed a few of these issues, and with reference to a climate data set. So we took this data from GCM, and it's a 25 by 25 square kilometer spatial grid. And we have about 4,000 grid points across this years, 1970 to 2000. So we had to compute really CCM for, so what is the idea here? We had precipitation and temperature readings at each grid point. And we want to really detect if, you know, the temperature at one point is actually driving the precipitation at the neighboring point and so on. So if you imagine the number of computations that you have to do with the vanilla CCM, it is really mind-boggling. So we built in parallelizations, and changed a few things, modified the way the CCM is computed. I'm not going to go into the details, but you can see an order of improvement as we made two changes. The way we compute CCM for different library sizes, we went on a log scale, so to speak, and we also did the parallelization. And again, this was a collaborative work with Udit, of a dual degree student. And just to give you an idea of the improvement, I showed you that. So we divided into 7 zones. I'm just going to show you the analysis that we got from this one zone. We picked this zone so that all of them are more or less at the same temperature. And this is the network that you get. And very importantly, when we are dealing with dynamical systems, please do not do an instantaneous analysis. Always do a lagged analysis, okay? Because they're going to be transients. So we did a lagged relationship, causal relationship analysis. And at low lags, the bidirectional causality exists between precipitation at spatially nearby points. And of course, stronger causal relations occur almost in the northeast direction. But if you go to large lags, the nearby causalities vanish, and the longer ones actually persist, which makes sense from a climate process viewpoint. Okay. So just wanted to conclude with this, and maybe 2 more minutes. Is it okay? Yeah, because I want to talk about tea. I don't drink tea. I'm sorry. I mentioned earlier that CCM, if you read original paper by Sugihara in 2012, it says that it's good for weakly coupled processes and so on. But what is weak, we don't know. So one of my students took up that aspect rigorously, and he realized that, and we went through that, he realized that rather than quantifying in terms of coupling strength, by the way, there is no definition of coupling strength. I searched the length and breadth of the literature. If you know something, let us know. Instead, we found a metric called synchronization likelihood. And I've given the reference here. This was proposed in 2002. Not giving the expression, it's a very big, intimidating expression. But he implemented this and very nicely did a rigorous analysis. This is on the 2D Hennen map. And the observations are as follows. If the synchronization level likelihood is in this range, by the way, it is a normalized one between 0 and 1. In this range, CMS fails, the convergent cross mapping fails to detect. Likewise, when it is very high, also it fails. So this is the comfortable range of synchronization likelihood over which the convergent cross mapping works. Okay, there is just one more paper, but it doesn't use synchronization likelihood to qualify the usage of CCM. but it uses something else, but it doesn't really go address the coupling strength aspect of it. This is only work. We have not published this yet, but some more work, rigorous work is needed because we have done this only for 1 or 2 systems. But the idea, the message is, if you pick a method, please ask if you can calculate something on the data to be able to figure out if it is suitable. If you take linear regression, for example, straight away look at the correlation coefficient and it'll tell you whether linear model is suited or not. You don't have to really fit a model and go through the entire analysis. Okay, so we did extend it to multivariate case. I'm going to skip that and then conclude with the synchronous networks that Udit talked about in the morning. I have to make Udit's statements come true. Arun will talk about it. Okay, so the synchronous networks do not belong to the correlation networks category nor the causal networks category. The reason is they are computed over a window of time instants, and they lack directionality. But you say that even if it is correlated over that window, of course, you have to really do a time shifting. And then, of course, there is a metric that I'll give you. If that happens, then you will say, here we are interested in synchronization of extreme precipitation. So the objective is to investigate, as Udit mentioned in the morning, spatio-temporal evolution of synchronous rainfall extremes, right, of the ISM. And this is the data. And this is the idea. So what we do is, of course, we identify extremes using 95 or 99 percentile. And then we consider a window. So the entire period is from 1901 to 2019. So we take a 10-year time window and then keep moving. But this 10-year time window is for data, not for calculating synchronized extremes. That is a much smaller window. We slide by 1 year. So overall, we have 109 years of data. This is what tells you the entire procedure. So you start with the data, identify extreme events using 99% or 95% percentile. And then you pick those points and then calculate the synchronization strengths. I'll give you the expression in the next slide. Once you have done that, then you apply a threshold and arrive at the adjacency matrix, and then you mine. Once you have determined the network, you mine the network. That's the idea. Okay, so here are the expressions. Of course, they are also available in our paper for calculating the strength of synchronization and the adjacency matrix. Now, once the network is reconstructed, these are the coefficients, right? These are the measures, some of the measures that we look at. I'll just show you one inference. So we look at degree distribution. So what does this map show? It basically shows the degree centrality across the country. The degree is really high in the central India. Okay, so this is, of course, local degree that we have calculated. This is across the country. Even as you throw away the other areas, they're very, very strongly connected. That means the extreme rainfall is really connected to the extreme rainfall here. They're very closely connected. What is this showing you here? The degree distribution. That means it's basically, it's a probability plot, right? Now, our objective, one of our objectives was to see if the degree distributions are changing, okay, over this entire period. And you can see they're hardly changing. You can see it's done over many, many years that we have done. And if that was just a visual eyeball reading, this is using a statistical analysis. So you can use Kolmogorov-Smirnov test or Jeffrey's divergence test to compare across distributions. And the conclusion is that the divergence of one distribution from another is very low. They're not identical, but it's statistically insignificant, the differences. That's the conclusion. Okay, so I'm going to skip this and end with acknowledgments. Many, many thanks for allowing me to go a bit overboard. And many thanks to all the students and collaborators and, of course, the departments and the funding agencies. Thank you. Tea, not time. Yeah, sure. Oh, yeah, sure.